In this video, we're going to investigate some basic concepts of a chi-square distribution and its applications. If a random variable zi follows a standard normal distribution with I starting from 1 to k, with each zi is independent of each other, the sum of the squares of these independent and normally distributed variables follows a chi-square distribution. K is the degree of freedom. Population mean mu is k, or the degree of freedom, while the population standard deviation sigma equals square root of 2 times the degree of freedom. The chi-square curve is skewed to the right when k is greater than 90. The chi-square curve approximates a normal distribution with a mean of a k and a variance of a 2k. There is a different chi-square curve for each k. In this diagram, blue curve corresponds to k equaling 1, orange corresponding to k equaling 5, and olive one corresponding to k equaling 10. One of the applications of a chi-square distribution is the goodness of fit test. For instance, if I guess my unknown data may fit a binomial distribution, I can use a chi-square test. The test statistic for a goodness of fit is as follows. The chi-square equals, now the OI minus EI, and I take a square and divide it by EI, and then sum up from I equal 1 to k, where OI are observed values, EI are expected values, k is the number of categories, and df is equal to k minus 1, or the degree of freedom. The hypothesis will look like this. The data fits an expected distribution. Or the alternative hypothesis is that the data is not consistent with an expected distribution. Here's an example. Medical experts claim high blood pressure distributions among older adults look like the following. 20% of the population have a systolic blood pressure greater than 180. 30% of the population have the blood pressure within the range between 130 and 180, while the rest 50% will have a normal blood pressure. A small country called Brandonland will test 100 older adults. Now they found the real distribution as follows. 12 people have blood pressure greater than 180. 43 have the blood pressure within 180, 130 to 180, and 45 will have a normal blood pressure. The question is, if the distribution is consistent with medical experts' prevalent estimate, my hypothesis will be like this. The data fits the expected distribution. Or the alternative hypothesis is that the data is not consistent with expected distribution. In this table, my expected number of sample, well actually we got 100 people in this sample. Based off of the estimate, 20 people will have high blood pressure, or the blood pressure, systolic blood pressure greater than 180. And 30 will be around the borderline between 130 and 180, and 50 people will have normal blood pressure. My chi-square will be calculated to be 9.33, and the p-value equals 0.01. Here's my conclusion. Since p-value equals 0.01, which is less than 0.05, we have to reject the hypothesis that Brandonland's data fit the expected distribution. The next application is to test independence. The test involves a contingency table. Oj is the observed value at row I and column J. Eij is the expected value at row I and column J. Ef is my degree of freedom, which equals number of column minus 1 times number of row minus 1. I have two assumptions here. First, both variables in the contingency table are categorical. Second, the sample data under investigation is random. Here's my hypothesis. Variable A and B are independent. My alternative hypothesis is that variable A and B are not independent. The formula of a calculation of expected values are row total for I times column total for J divided by grand total will be equal to expected value at row I and column J. Here's an example. Now, I have a contingency table of hedge fund type by continents. There are 3 hedge fund types: long only, short only, or long short mixed. And all these hedge funds may be located in continent Europe, North America, and Asia. My hypothesis will look like this. Continents and hedge fund types are independent. The alternative hypothesis will be that continents and hedge fund types are not independent. Now, based off of my calculation formula, I have to use the row total for row 1 times the column total at column 1 and divide by the grand total, which is 1,245. And my expected value at row 1 and column 1 equals 233.91 based off of this formula. And similarly, I can calculate all of them. And then my chi-square can be calculated, which is 32.13. And then my p-value can be found as 0.000018. Here's my conclusion. Since my p-value is 0.000018, which is less than 0.05, we can reject the hypothesis that continents and hedge fund types are independent. There is a relationship between continents and hedge fund types. Our final application is the test of homogeneity. If we need to test whether two populations have the same distribution, maybe the distribution is unknown to us. So our hypothesis maybe look like this. The distribution of two populations is the same. And the alternative hypothesis will be the distribution of two populations is not the same. And we're going to use the similar formula to calculate chi-square. Within this formula, Oj is the observed value at row I and column J, while Eij is expected value at row I and column J, and df equals number of column minus 1 times number of row minus 1. Here's my special requirement. All values in the table should be greater than or equal to 5. I have a similar calculation of expected values. Row total for I times column total for J divided by grand total will give me expected value at row I and column J. Now, here's my example. What I'm trying to do here is to investigate the concentration of investment or the distribution of the concentration of the investment before and after COVID-19. I have 4 sectors here: technology, industrial, retail, healthcare. And my expected values can be calculated based off of the formula outlined above. And then eventually I will have this chi-square, which is 10.13, and the p-value, which equals to 0.02. My conclusion will be, since the p-value equals 0.02, which is less than 0.05, we can reject the hypothesis that the distributions of a concentration of investment are the same before and after COVID-19 hit. In other words, investment interest has changed since the outbreak of COVID-19. Thank you for watching our video. If you like our program, please subscribe to our channel.